Let's talk about the Simpson rule. The last videos we talked about the trapezoidal rule. This was an idea how to do numerical integration, and now we develop that idea. And it's a really small step. If you understood the trapezoidal rule, then you will easily understand the Simpson rule. What was the idea behind the trapezoidal rule? We had a function, we had an interval on which we want to integrate. We took some points between a and b, the first point to be a, the last point to be b, and these points linearly spaced. And then we evaluate at these points. And then we assume that these points are connected by straight lines. And then we take the area under these straight lines to be the area under the curve. And the formula will give us the integral value is h, this distance, times the first value halved, then all the values in between, and the last value again halved. And what do we have? We have a weighted sum of the function values. H halved, h, and h halved are the weights. Okay, and now what is the idea of Simpson? We do the same. The first point is a, the last point is b. This is the integration interval. And then linearly spaced, all distance the same, we evaluate the function. And then what is the new thing? Instead of interpolating with straight lines, we can use 3 points, and then we can find the parabola interpolating these 3 points. How would that look like? And then we integrate these parabolas. And what will we get? We will get a formula which looks like as that, but with some modified weights, and that's all what will change. Okay, and now is the question, how can we find these weights? And in one of the last videos we did what we can now reuse. We have 3 positions and 3 function values, and what are we looking for is the formula for the interpolating polynomial of degree 2. And this is the answer, and that we can reuse. For the moment we use -1, 0, 1, but we can easily generalize. Okay, here we have the value y -1, the value y 0, and the value y1. And the interpolating polynomial is, this is the leading coefficient, this is the coefficient for x, and this is the absolute value of the parabola. And now we can integrate. Last time we differentiated, and we integrate on that interval, so from -1 to 1. We need the antiderivative. This is a constant, x cubed divided by 3. So we get a divided by 3, a half divided by 3 is 1 divided by 6, a third, and 1 divided by 6. Then this part we get a x squared divided by 2, and so a half divided by 2 we get a quarter. And here we get a y0 times x. And then we have to evaluate at position 1 and at position -1, and we have to take the difference of that. So we get a 1 is a 1 here we have, and a 1 here we have y0. Then minus a -1, then we get a minus, so we have a plus. Then here a -1, then we get a minus, And here a -1 we get a minus, and the minus from the beginning is a plus. And now let's collect 1 divided by 6, y minus 1. Once again is 2 divided by 6. And here we have minus a quarter, here we have plus a quarter. So it's 2 divided by 6 times y minus 1. Now let's collect the y0 parts. Minus 1 divided by 3 minus 1 divided by 3 is minus 2 divided by 3. Nothing from here. Plus 2. Minus 2 divided by 3 plus 6 divided by 3 is plus 4 divided by 3. And the y1, 1 divided by 6, 1 divided by 6, 2 divided by 6, plus minus, so it's 2 divided by 6. And so if we scale by age, then we get, and you get for arbitrary interval, it doesn't matter if this is 0, 1, minus 1, or if it's 20, 21, 22, or if it's 31, 31.1, 31.2, we can write, we get an age, and we get 2 divided by 6 is 1 divided by 3, yk, plus 4 divided by 3, yk plus 1, plus 1 divided by 3 times yk plus 2. And so we have our formula for one interval. If we have more than one interval, then in this case we have 3 parts, and then we get h times 1 divided by 3 y0 plus 4 divided by 3 y1 plus 1 divided by 3 y2. That's for the first part. And then we have the second part plus h times 1 divided by 3 y2 again, plus 4 divided by 3 y3. And for the last part, and so we get 1 divided by 3, 4 divided by 3, 2 divided by 3, 4 divided by 3, 2 divided by 3, 4 divided by 3, and 1 divided by 3. That is the formula we were looking for. And now we can also factor out a 3, and then we get what I wrote in my script. This is the Simpson rule. So we divide in n pieces of the same length, but now n must be an even number. It's not possible to have 5 parts. It was possible using the trapezoidal rule. If you're using the Simpson rule, this configuration is not allowed. If this is A and this is B, then this is not allowed. We need one more point. And then we split our interval as we did last time. We evaluate as we did last time. And then we get that formula. Here I reordered the factor 4 and the factor 2. And we have the formula which we had on paper, and we have a formula of the same kind as we had for the trapezoidal rule. But what is the difference? The weights are a little bit modified. Let's have an example. And again, let's integrate e to the minus x on the interval 0, 2. So what do we have to do? First we have to choose an n, where n is an even number. Odd numbers are not allowed. And for example, we can choose n to be 6. That's the same choice we had for the trapezoidal rule. There we integrated the same function on the same interval. So this gives us h is 2, integration interval, the length of it divided by 6. So we have 1 divided by 3. Then we have xk, which is a plus k times h, so it's 0 plus k times 1 divided by 3. And so we get and the corresponding y values, we get e to the minus 0, e to the minus a third, e to the minus 2 divided by 3, and so on. Using electronic help, we get 1, and we get these values. And now let's apply our Simpson rule, and we get h divided by 3, that's the formula in our script, times the first value unmodified plus 4 divided by 3 times the second value plus 2 divided by 3 times the third value, and so on. So it starts with weight 1, and then 4 divided by 3 is second, and 4 divided by 3 again is the weight before the 1 weight, and then 2 divided by 3 and 4 divided by 3, so on. Now use electronic help to do that calculation, and you will get 0.86472324. And what is the correct value? The correct value is 8646641. And so we are correct. If rounded to 4 digits after the decimal point, we are correct to this 4th digit after the decimal point. And so we have a wonderful approximate value. Last time, using the trapezoidal rule, we were not that good. Here we had 8,7. And so in this example, at least in this example, Simpson performs much better. And normally Simpson is superior to trapezoidal rule, but not in every case. We will study that in the next video. So this was our video about the Simpson rule, and I think it's not too hard to understand. And in the next video we will talk about the properties of Simpson rule. And a last remark, Simpson rule is often called Kepler's Fassregel. I don't know how to translate to English. Fass is something of wood, and you have beer in it or wine in it. This is a Fass. And this rule is also called Kepler's Fassregel. Maybe Kepler had this idea for doing the integration, and Simpson as well. And so I don't know why some people call it Kepler's Fassregel and others call it Simpson rule. Okay, this was our video about the Simpson rule.